Hello, in this video we're going to talk about uniform continuity. So first we're going to discuss the definition of uniform continuity, then we'll go over a couple of examples, and eventually we'll talk about the Heine-Cantor Theorem, which tells us some specific continuous functions are also uniformly continuous. But first, what is uniform continuity and why do we care about that? So the reason we care about uniform continuous functions becomes more and more clear as we discuss later material. Specifically, when we discuss integrability, that becomes very clear as to why we need this concept. Okay, so what is the definition? Think about what the definition of continuity is. Continuity means if you have a sequence, let's say un, that approaches u, then f of un also approaches f of u. So in that case, we say the function f is continuous at the point u. Now, if you can sort of think about the exact same idea, but all over the entire domain. What does that mean? In other words, if you have two sequences un and vn that are close to each other, you would like to make sure that the functional values are also close to each other. Not necessarily that you have a sequence converging to one thing, but you have two sequences that in some ways they are converging to each other. In other words, you have two sequences that are getting closer and closer to each other, then the functional values f of un and f of vn are also getting closer to each other. So let's look at the definition now. A function f from D to R is called uniformly continuous if every two sequences un and vn in D satisfy the following. If limit of un minus vn is equal to 0, then limit of f of un minus f of vn is equal to 0. So first, a couple of examples. If you look at the function from R to R defined by f of x equals to x, we want to see if this is a uniformly continuous function. So what we want to do is this. We want to see what happens if un minus vn is equal to 0. Can we deduce that f of un minus f of vn also approaches 0? And the answer is clearly yes, because f of un is un and f of vn is vn. So the answer is then yes. The function is in fact uniformly continuous. So suppose un and vn in R satisfy limit of un minus vn equals 0 as n approaches infinity. Then limit of f of un minus f of vn as n approaches infinity is equal to the limit as n approaches infinity of un minus vn. F of un is un, f of vn is vn, and of course this is 0. Thus f is uniformly continuous. So that's the first part of the example. If you look at the second function is also uniformly continuous, because if you look at un minus vn and assume that un minus vn is approaching 0, so let's see what happens. So let's start with suppose un minus vn. Well, un and vn are in that interval, are in 0, 1, such that limit of un minus vn is 0 as n approaches infinity. Now we're going to look at f of un minus f of vn. What we need to show is that this also approaches 0. If you look at this one, f of un is un squared, f of vn is vn squared. And if we factor this one, we get un plus vn, un minus vn. Now, the key point is this. Un minus vn approaches 0, but un plus vn, even though un plus vn doesn't approach 0, but it is bounded. And the reason is un and vn are in the interval from 0 to 1. So if I put absolute values here, then I can in fact use comparison lemma. Un plus Vn is less than or equal to 2. Un minus Vn approaches 0. So by the comparison lemma, limit of f of un minus f of Vn is in fact 0 as n approaches infinity. And this tells us that f is uniformly continuous. And that's the end of the proof. So these were two examples of functions that were uniformly continuous. Okay, let's look at a couple of examples of functions that are not uniformly continuous. The following functions are not uniformly continuous. Notice the similarity between function in part A and function in part B of the previous example. So almost identical. F of x equals x squared, that part is identical. The only difference is the domain. The domain of this one is all real numbers. The domain of this one is 0 to 1. So let's look at the graph of this function and see why one is uniformly continuous and the other one is not. If you look at the graph of this function, and perhaps I would have to draw this one steeper. If I look at the first one, which is from 0 to 1, then anytime you have two sequences that are close to each other, which is basically this is the run, their rise has a limit on it. And since the rise cannot go to infinity, the difference would remain, would approach 0. But if I look at the entire function from negative infinity to infinity, you could have sequences that the rise is small, but the run is very large, because the graph becomes very steep. So because the curve is very steep, I could create sequences un and vn that un minus vn approaches 0, but un squared minus vn squared, which is un plus vn times un minus vn, doesn't approach 0. And now we'll have to get to the algebra of it. We could create that by making sure this is large, although this is a small. So maybe let's make this one n and make this one 1 over n. Then the product is going to be 1. So given that, we can create un. Un would be the average of n and 1 over n, and vn would be the difference over 2. So let un be n. You can create a bunch of examples. It doesn't have to be exactly this, but this is one example. And vn be 1/2 n minus 1 over n. If we look at un minus vn becomes 1 over n, which approaches 0. If we look at un squared minus vn squared, that is un plus vn, un minus vn. un plus vn is going to be n, and un minus vn is going to be 1 over n. And that clearly does not approach 0. And therefore, f is not uniformly continuous. Again, think about uniform continuity as starting from a sequence, two sequences. If the two sequences are close to each other, then their functional values must also be close to each other. So we created an example of two sequences, un and vn, that un minus vn approaches 0, but f of un minus f of vn doesn't approach 0. Therefore, the function is not uniformly continuous. Okay, the second example is a function from open interval 0, 1. So if you look at this one, the interval is in fact a bounded interval, unlike the first part, unlike part A. However, there is an issue at 0. the 1 over x blows up at 0. So if you look at the graph of the function, you can see what I mean by that. So the graph of the function looks like this. So at 0, even though the two sequences un and vn are close to each other, the functional values could be very far from each other. So we need un minus vn to approach 0 and 1 over un minus 1 over vn to not approach 0. So we can create examples of this sort. So if you simplify this, you get vn minus un over un times vn. We can make sure un and vn are roughly 1 over n. So let's say let un be 1 over n and vn be 1 over 2n. Although since I want to make sure that the entire sequence is within the open interval 0 to 1, I probably have to start from 1 over 2n and 1 over 3n. Just to make sure 1 over 1 doesn't appear in the sequence. Now, un minus vn is going to be 1 over 6n, which approaches 0. F of un minus f of vn is going to be 2n minus 3n, which is negative n, and that does not approach 0 since negative n is unbounded by the Archimedean property. Therefore, f is not uniformly continuous. So we gave examples of two functions. One is not uniformly continuous on the entire real line. The other one over a bounded interval, but still that also has an issue at 0 and it is not uniformly continuous. Next, we're going to talk about a simple fact that every uniformly continuous must also be continuous. So we're going to go over the proof of this one. So if f from D to R is uniformly continuous, then it is also continuous. So if I were to show that this function is continuous, I would need to show for any sequence that converges to a number, let's say x naught, f of that sequence converges to f of x naught. So let's start with let xn in D converge to some x naught in D. I would have to show f of xn approaches f of x naught. In order to be able to use the uniform continuity, I need two sequences. So what I know is, again on the right, I'm going to look at the scratch work. What I know is this, and what I want to show is f of xn approaches f of x naught. For us to be able to use uniform continuity, we need two sequences that are close to each other. So the way you can create the two sequences, if you think about that a little bit, you will see you can rewrite the first condition as xn minus x naught approaching 0, and the second one f of xn minus f of x naught approaching 0. So now this should be clear what we need to do. This would be our second sequence. So essentially I'm just going to take the second sequence to be the constant x naught. Let yn equals x naught be a sequence, just a sequence of constant x naught. Limit of xn minus yn becomes limit of xn as n approaches infinity minus limit of xn is just yn is just x naught, so that's x naught minus x naught, which is 0. If you look at limit of f of xn minus since we know that f is uniformly continuous, so since f is uniformly continuous, when we look at limit of f of xn minus f of yn, we get, as n approaches infinity, we get the limit of f of xn minus f of x0. We know this would have to be 0. This is 0. Okay, so that means, so since xn minus yn approaches 0, f of xn minus f of yn must approach 0. Thus, if you take a look at f of xn as n approaches 0, this becomes limit of f of xn minus f of x0 plus f of x0. And this becomes 0 plus f of x0, which is f of x0. So therefore, f is continuous at x0. And this finishes up the proof. So what we showed is that if a function is uniformly continuous, then it would be continuous. Okay, so you could ask whether the converse of this statement is true. Clearly the converse isn't true. If you look at the previous example, we had two functions, f of x equals x squared, that was continuous, and but it is not uniformly continuous. And also f of x equals 1 over x, that was continuous but is not uniformly continuous. However, when we fixed the first one and we fixed the interval, instead of having the interval from negative infinity to infinity, when we changed that to the interval from 0 to 1, closed interval from 0 to 1, it became in fact a uniformly continuous function. So perhaps a fix to make sure a continuous function is also uniformly continuous is to make sure its domain is a closed and bounded interval. And in fact, that is true. So the Heine-Cantor theorem tells us that if you have a continuous function over a closed and bounded interval, it is uniformly continuous. Okay, so what do we know? We know our function is continuous. And what are we trying to prove? We are trying to prove that the function is uniformly continuous. Think about what the definition of uniform continuity is. The definition of uniform continuity is if you have two sequences un and vn that the difference approaches 0, then the functional values, the difference of the functional values also approaches 0. So we will start from two sequences. So let un and vn in the interval a to b be sequences such that limit of un minus vn is 0 as n approaches infinity. So I start from un minus vn approaching 0, and I want to show f of un minus f of vn approaches 0. So this is the objective. I know this one, and the objective is to prove f of un minus f of vn approaches 0. How do we do that? So, and of course in the process we will have to use the fact that f is continuous, and also the fact that the domain is a closed and bounded interval. Okay, so f continuous. Continuity of f means if you have a sequence approaching some number, let's say a0, then f of an approaches f of a0. In order to be able to use that, we need a sequence that is convergent. Okay, so we'll have to extract convergent sequences. And that is where we could use the sequential compactness theorem again. So when you have a sequence that is inside a closed interval, we can create sequential compactness. We can apply sequential compactness and create a subsequence. However, even if we show for a subsequence f of u n k minus f of v n k approaches 0, that's not enough to show f of u n minus f of v n is approaching 0. So what I'm going to do is I'm going to first deal with the fact that I need to prove f of u n minus f of v n approaches 0. Let's see what happens if it doesn't approach 0. So on the contrary, assume limit of f of u n minus f of v n is not 0. We had an exercise that if a sequence doesn't approach a number, it would have to be kept away from that number. So this is the exercise. By an exercise, there is a positive epsilon and a sequence of natural, or I guess it's a subsequence of natural numbers nk such that f of u sub nk minus f of v sub nk in absolute value is greater than epsilon. And this is true for all k. Now I will choose a subsequence of this subsequence that is convergent. So by the sequential compactness theorem, there is a subsequence u sub mk of u sub nk such that u sub mk converges to c for some c inside the interval a to b. Because we know closed and bounded intervals are sequentially compact, which means every sequence inside that interval has a convergent subsequence. Okay, now we can apply the continuity of f. Since f is continuous, limit of f of u sub mk is f of c as k approaches infinity. Okay, so we know that this guy approaches, at least a subsequence of that, approaches f of c. But how about this one? If this also approaches f of c, then that would be problematic. So if we think about the condition that we had at the beginning, I haven't actually used the fact that un and vn are close to each other. So we know this. Since limit of un minus vn is 0 as n approaches infinity, limit of u sub mk minus v sub mk as k approaches infinity is also 0. Now, umk approaches c, therefore vmk must also approach c, and that's not very difficult to see. If you look at vmk, this is going to be limit of umk as k approaches infinity minus limit of umk minus vmk. The first one is c, umk approaches c, and the second one is 0. So now again, since f is continuous, limit of f of vmk is also f of c as k approaches 0. So we showed f of umk approaches f of c, and f of vmk approaches f of c as well. Therefore, limit of f of umk minus f of vmk as k approaches infinity is equal to, the first one approaches f of c, the second one also approaches f of c, and that's 0. However, this contradicts star. Star told us, I'm going to call that star, that the difference between f of u and k and f of v and k is always more than epsilon. But if it approaches 0, the difference cannot be away from 0. The difference cannot be more than a fixed epsilon. So here what we proved was the Heine-Cantor theorem, which is if a continuous function has a domain that is bounded and closed, then it would be uniformly continuous. A very important theorem. Okay, so if you would like to continue with this class, feel free to subscribe, and I will see you in the next video.